Hello everyone, here is Karam. In this video, we will learn how to use Fluent to perform time-dependent or transient simulation. In this tutorial, we will simulate a fluid flow around a cylinder with a Reynolds number of 100. Vortex shedding will be observed. The goal of this simulation will be to visualize the transient vortex shedding behavior around the cylinder. Now, open the Fluent Launcher window and ensure meshing mode is selected. After that, force solver processes recommended for this tutorial. After that, click Start. Then select the workflow type and select watertight geometry. Then click on Import Geometry and select the file format, the units, and the file name. Set units to meter and then select the geometry and then click OK. The next step is to add local sizing. Body of influence will be defined in the meshing step. A BOI, body of influence, has been defined in the CAD file to enforce good mesh resolution in the proximity of the cylinder and the downstream wake region. So in this step, we will click yes and then select body of influence and the growth rate 1.2 and the target mesh size will be 0.25. And then select by zone, not label, and then select the BOI region and then add local sizing. The next step is to generate the surface mesh. Keep the default minimum maximum sizes and the growth rate, but change the normal angle to 12 and change the size functions to curvature and change the curvature normal angle to 12 degrees and then click generate the surface mesh. As you can see here, we have a finer mesh in BOI region. Maximum skewness is 0.39. Now describe geometry. The geometry consists of only fluid regions. So set the geometry consists of only fluid regions with no voids. And then click describe geometry. Then we need to change the type of boundaries as required. So here we have velocity inlet and here we have pressure outlet. These symmetry and the cylinder will be wall. And then update boundaries. Zone will be a fluid region, so click update region. Then we need to add boundary layers, so change the offset method to uniform and the number of layers to 15. The growth rate will be 1.2 and the first height will be 0.02. Then click add boundary layers. After that, generate the volume mesh, keep the fill with polyhedra and keep the default settings as they are and generate the volume mesh. And here is our mesh as you can see, and we can see here the boundary layers. The minimum orthogonal equality is 0.38, which is very good. The next step is to save and write the mesh file. So select the type of mesh file as .mesh.gz and name it cylinder BOI and click OK. And now we can click switch to solution and click yes. As we said earlier, the four primary tabs used in every simulation are domain, physics, solution, and results. Now, from the domain tab, click on check and then perform mesh check. And you will see here the minimum volume is a positive number and checking mesh is done. So the mesh check returns no error messages. And the quality was already verified in meshing mode. Now, in the physics tab, the time will be transient and the solver type will be pressure based. The Reynolds number based on the cylinder diameter is 100, so the flow is laminar. Now, regarding the models, this will be laminar flow. As we said, the Reynolds number is 100, so this will be laminar flow. Click OK. Now click on material and then set the density to 1 kilogram per cubic meter and the viscosity to 0.01 kilogram per meter second. And then click change create and then close. Materials definitions are complete, so proceed to zones. The default material of air will be used, so no need to set any cell zone conditions. So as you can see here, the cell zone conditions is set to air, so there is no need to change anything. So click close. Now go and set boundary conditions. Double click on inlet and set the velocity magnitude. This will be 1 meter per second and click apply close. The outlet will be at 0 gauge pressure. There is no need to change anything. Click close or apply close. The cylinder is walled and these 4 boundaries are symmetry boundaries. No input required for symmetry boundaries. And now boundary conditions are now complete, and so to setting up physics. Then go to the solution tab and click methods. The pressure velocity coupling scheme will be BISO and the transient formulation bounded second order implicit. Now, BISO is recommended for most transient cases because symbol may require more iterations to converge at each time step. Bounded second order implicit is recommended when time accuracy is important. The next step is click on controls and change the under relaxation factor for pressure to 0.7. Now Fluent recommends using values of 1 for the pressure and momentum under relaxation factors when using BISO. However, in many cases that proves to be too high, causing the solution to diverge. In many cases, a range of 0.7 to 0.9 will often work. Here, a value of 0.7 is selected because it is more likely to be stable. Trial and error can be used to find the highest possible value that will work in any given case. Because in general, a higher value means the solution will converge in fewer iterations per time step. But for small cases such as this, the benefits may not justify the additional upfront effort. The next step is to do initialization. Select standard initialization and compute from inlet, and then click initialize. While hybrid initialization is often the best choice for steady-state problems, it is not always suitable for transient problems, where the initial condition is part of the problem definition. In this case, it will be easier for the solution to achieve unsteady behavior by using a uniform velocity field. The next step is to do a click on cell registers and click new and select region. This will be region batch, and the input coordinates x minimum will be 0, x maximum will be 15, and y minimum minus 9, y maximum 9, z minimum minus 0.5, and z maximum 0.5. And then click Save Display, and then click Close. After that, click Batch, select the y velocity, and select Region Batch, and then select the value 0.18 and click Batch, and then Close. From the Results tab, click on Vectors and then New. Select the surface symmetry A, and then click Save Display. Change the scale as required and also adjust the style according to your geometry. click on monitors and then residual, and then change iterations to plot to 100, and then click OK. After that, click on run calculation, and the time step size will be 0.1 and the number of time steps will be 120. Now save the case and data file, and then click calculate. Now let us see the velocity vectors. Then the next step is to do additional time steps, because the cyclic behavior will become more regular after first 5 or 6 cycles. So go to solution and change number of time steps to 600. And click calculate. And the solution is now completed. The next step is to create a new mesh, vector, and contour objects. From Results tab, click on Mesh and click New. After that, select the cylinder and the inlet and the outlet and symmetry 1 and 2. And select Edges and Edge Type All, and then click Save Display. And then click Close. The mesh surfaces form an outline of the computational domain. Now let us create vector. Click on vectors and then New, and then select global range and not auto range, clip to range, and auto scale. And minimum will be 0 and the maximum will be 1.3. Then select symmetric A and then save display. This will be filled arrow. Color map option, float, apply, close, save display, close. Now from contours, click new and tick filled, node values, global range, and clip to range. And then the minimum will be 0, the maximum will be 0.9. And this will be dynamic pressure. And the surface will be symmetric A, and click save display. Color map option, float, apply, close, save display, and then close. Now we will go and make scene object. Click on scene, new, and then this will be contour scene, and select contour and mesh, and click save display, and then click close. Now another scene, and this will be vector scene or vector object, and this will be vector 3 and mesh 1, and then click save display and then close. The next step is to define solution animations. From calculation activities, right click on solution animation and click new. Then name this to contour animation and record after every one time step, and this will be the contour scene. and this animation view will be front, and then click OK. And define another one, click new, and this will be vector animation. Select the vector object, and this will be front, and then click OK. The next step is to do autosave. From solution, click on from activities panel, click autosave. When performing a transient simulation, Fluent doesn't store the entire time history of the solution. So if it is desired to post-process data from any intermediate times, data files must be saved at those times. So we will set the interval to 5 time steps, save data file every 5 time steps, and then we'll click OK. The next step is to click on methods and select non-iterative time advancement. And after that, select the scheme fractional step. Neta is an algorithm used to speed up the transient solution process. Now you are ready to start calculating, but first save case and data files as cylinder unsteady Neta. Write case and data, and this will be and then click OK. Keep the 0.1 time step size and type the number of time steps 240 and click calculate. And the calculation now is completed. The next step is to click on animation and then playback. Now select the animation sequences contour animation and then write record video file and select video option. This will be MP4. Deselect use stored view and then click write. And here, as you can see, the video has been exported successfully. And here we have finished, but let us see the animation first. And here we have finished for this tutorial. Thanks for watching. See you soon in another video. Goodbye.